The human body is a highly efficient, tightly calibrated machine, but it is entirely composed of soft tissues and brittle calcium. A single misstep under high physical stress can shatter bone, tear muscle, and wear down cartilage. For most of human history, that kind of physical damage meant a permanent loss of capability. Medical fixes were strictly structural. A heavy wooden splint or a basic crutch could bear weight, but they were lifeless tools. They failed to replicate the exact tension of a ligament or the complex multi-axis physics of a joint. To genuinely repair the body, engineers had to stop treating it as biological tissue and start treating it as a mathematical translation problem. They mapped out kinematics, tracking exactly how far a knee bends or ankle rotates during a stride. This real-time chart shows kinetics. As the wireframe steps, data visualizes the invisible forces, tracking exact pressure spikes and shifting weight loads on the joints. By isolating those precise force loads and joint angles, engineers no longer had to guess how a leg absorbs an impact. They extracted a flawless digital blueprint of human movement. Extracting the math is only half the equation. To replace a shattered femur or a deteriorating spinal disc, that digital data has to be translated back into the physical world. Researchers use material science to develop specialized biomaterials, like titanium alloys and porous polymers, engineered to explicitly mimic the natural flexibility, weight, and tensile strength of living bone and cartilage. An artificial hip joint or a 3D printed orthotic insole is milled to perfectly match the host's kinetic profile. The implant bears weight and distributes stress exactly like the tissue it replaced. A severe physical trauma no longer requires weighing a patient down with a stiff, heavy brace. We can now rebuild the structure to completely restore a patient's baseline physical capability. Replacing a stationary bone is a matter of structural engineering, but walking, running, and adjusting balance are highly unpredictable, dynamic actions. If a lifeless machine cannot adapt to a sudden shift in weight or uneven terrain, it acts as dead weight, forcing the living host to drag it along. To fix this, developers embed control systems. Highlighted nodes track spatial orientation at contact. As the base strikes uneven terrain, sensors transmit data to a processor in the knee, instantly adjusting the mechanical joint's angle before the next step. The hardware is an active participant. It calculates and reacts alongside user biology in real time. This mechanical assistance changes the medical approach for patients recovering from severe strokes or neuromuscular damage. Instead of physical therapists manually supporting a patient, rehabilitation robotics envelop the limb. The machine provides calculated physical resistance and guides the arm through perfectly precise therapeutic motions. These same assistive principles scale down into daily health protection. Smart clothing and lightweight exosuits monitor posture, detect physical instability in the elderly, and lock joints or adjust tension instantly to prevent falls. By collaborating with a struggling body rather than just forcing it to move, these systems actively teach the human nervous system how to heal itself and regain motor function. If a machine can perfectly sync with the body to restore baseline health, there is no structural reason to stop at natural biological limits. The human-machine interface bypasses physical movement entirely. It connects devices directly to the human nervous system, allowing users to control machinery through electrical nerve signals alone. Military applications utilize these neural connections in exoskeletons, allowing soldiers to bear extreme weight, multiplying their endurance and raw lifting strength far beyond human capacity. In sports science, advanced biomechanical models analyze exact joint stress to optimize athletic form. Competitors use this data to push physical output past historical records while minimizing the risk of tissue failure. Biomechanical technology now functions as an enhancement tool, allowing entirely healthy users to augment their physical capabilities on demand. The physical boundary separating human biology from engineered machinery is disappearing. Engineers are designing brain-controlled prosthetics equipped with AI feedback loops. These systems predict a user's physical intentions and execute the mechanical movement before the user consciously moves a muscle. The integration is happening at the cellular level. In biohybrid robotics, engineers cultivate living biological tissues in a lab and weave them directly onto metallic grids and mechanical systems. On an even smaller scale, nanomechanical implants are currently being designed to autonomously navigate the human bloodstream, identifying and performing physical repairs directly on individual cells. We have moved past using these systems as a medical safety net. Biomechanical technology is allowing humans to step away from being simple tool users and become the active architects of our own biology.